Hello, class. This is a recorded lecture for section 5.2, and this is graphing polar equations. And they're a little bizarre. Again, because you're not used to taking a look at a graph like this. And so again, the idea of this transformation going from rectangular or Cartesian to polar, the benefit is that if you have a bunch of curves, circles, curvy lines, it's much easier to write a polar equation for that than it is a Cartesian equation or a rectangular equation. And so you'll see that circles and weird looking curvy shapes are much easier represented in the polar plane than it is in the rectangular plane. So what we're going to do is just walk through a few of these and use technology too. What's nice now is there are nice graphing programs. I'll show you Desmos on how you could take a look at these. And so first thing we're going to do is the graph of the polar equation. And as I alluded to, you can see here on the right side, where you're going to use this polar graphing type of paper where instead of the X and Y, we have radius, which are these concentric circles of R1, 2, 3, 4, 5. And then you could see that you could split up the angles coming all the way around. I typically split it up into just pi over 4. But you can see this paper has the 30 and the 60 degree, right? Pi over 6 and pi over 3 as well. So what we want to do is to use this type of graphing paper to graph some of these equations. And the first one we always start with is the graph of a circle. And this idea of r equals 3, which implies theta can be any number, right? So if you think about it and you look at the Cartesian or the polar coordinate system here, if you looked at these concentric circles, you would go at r equals 3 and just follow that all the way around. And so if you tried to graph that, here we go. I clicked the wrong slide, sorry. You can see r equals 3, and it doesn't matter what theta is. And you could see, if you think about manipulating an equation, r equals 3, once you understand the coordinate system, it's a much easier equation to represent a circle than x squared plus y squared equals 9, right? With regards to radius squared, right? So that would be the Cartesian coordinate representation of that circle. So what about if we take a look at another equation? And I like to always do one for you by hand. So let me do this one. Let's see here. So what I'd like to do is let's do this one. Let's say r equals 2 times a cosine of theta. And so the strategy that we don't want to get away from is we could always generate a little table, all right? And so as you could see in analogous, the independent variable is theta, and the dependent variable would be r. So you plug in a value for an angle, and out will come a number. In this case, we have this value a, and you'll see why I picked a in this case when we get to that point. And so when you plug in 0 for theta, what do we get? Well, cosine of 0 is 1, and so this would be 2a. So if you think about it, right? And you know what? I'm going to change my mind here. Let's get rid of the a and just pick a 2. So this would be 2. All right. So if you think about the concentric circles, and let me just draw them in red. This would be 1. This would be 2. So let me plug the green point here. It would be right there, right? X equals 0, R equals 2. So let's pick another one. And what I'd like to do is I'll do what the book does. So the book does 30 degrees. So let's do 30 degrees. And so what is cosine of 30 degrees? Well, if you get out your sheet, so cosine of 30 degrees is square root of 3 over 2. So that would be 2 times square root of 3 over 2. And you see the 2's cancel, and you get square root of 3. And if you looked, got your calculator out and got square root of 3, that's about 1.7 and some change. So at 30 degrees, which might be about right here, it would be right there. And so now we'll do 45 degrees, and I'm just going to keep it on the green if you don't mind. And so what's cosine of 45 degrees? That's square root of 2 over 2, right? And so when you cancel that out, that's square root of 2, and that's about 1.4. And so let me get this one better. 1.7 is closer to 2 than 1, right? So that would be about right here. And then at 45 degrees, we're about halfway. So say like that's right here. And so what would be the next one? Well, the next one here would be 60 degrees, right? And so if we do 60 degrees, what do we get? Well, 60 degrees is 1/2, right? Times 2. 2 times 1/2, yep. And so that would give us 1. So at 60 degrees, it'd be about here, which is 1. So if you start connecting the dots, it's going to go like that. And then what's next? Well, what's next is 90 degrees. And 90 degrees is 0. And so 0, 2 times 0 equals 0. And so with the radius of 0, you just come back right here. And so this looks kind of like a half circle, right? So far, so good. So let's go to the next one, which you add 30 more, it'd be 120. So in this case, cosine in the second quadrant is negative. So cosine of 120 degrees would be minus 1/2, right? So that would be 2 times minus 1/2 would equal minus 1. And so here's the tricky part, right? So if you think about it, and let me put this one in orange. So if you're thinking about it, right, it'd be minus 1 and 120 degrees. You would think it would go right here, but that's actually plus 1. So what's weird about it is the minus 1 adds what? 180 degree phase shift. So it moves to the fourth quadrant. So really what this point here of minus 1 and 120 degrees would actually be minus 1. And if you added 180 to that, that would be 300 degrees and plus 1. Those are the same points. So when you flip that over, what ends up happening is you flip that over and it would go, as we make our thing here, it would be 300 degrees would be about right here, right? And then you would see the same thing happens here. If you do 150 or 135 first, 135, you would see again we get negative, and then in this case it would be square root of 2 over 2. So it'd be 2 over minus square root of 2 over 2. And again, you get the up here, but instead of that, you would get minus square root of 2. And again, it would flip and it would look like this. And then the same with at another, so that would be 150, right? 60, yeah, and then 180. We end up back to the same spot, right? So this one would be 2 times minus the square root of 3 over 2. And that would be minus the square root of 3. All right, and that would be about right here. And then the last one would be 2 times minus 1, right? And that would be minus 2. So you see here, this would be at this point here. And if you flip it back, it would come back here. And so it'd look like a circle that looks like that. And that is a kind of a crappy circle, sorry. But the idea here is this is a circle, right? And where is the center? Well, it looks like the center is if we think about our Cartesian coordinate, is that y equals 0, right? And x equals 1. And our radius here is 1, right? Because here's our center would be right there. And so long, laborious process and doing that graph. But if I show you here on Desmos, let me pull up Desmos real quick. Whoops, wrong button. So what was our equation? Our equation was R equals 2 cosine of theta. R equals 2 cosine of theta. And again, you see it gives you a nice representation, right? And so you can see our center right here is at 1, and the radius is 1 as well. So it gets out to 2, comes around here. So this is from 0 to 90 degrees is the top half of the circle. And then the second half of the circle goes from 0 to 180. And guess what happens? If you go back and go from 180 to 270, you just rotate again, and then you rotate again. And so you see that sometimes that when you do the polar coordinate system, you're going to get a graph right on top of one another. And so, for example, if we so let me show you a couple more graphs. So what if we change cosine to sine? So what would end up happening is R would equal, say, 2 sine, and then you type in theta to get theta to come up. There's theta. Whoops, I forgot my equal sign. There you go. And so you can see that this one is still a circle, but now we're moving the center to 0, 1. And if we did the minus, you would see that we would shift it 180 degrees. So sine of theta. And you can see it pushes it down. So I would highly recommend getting familiar with using either your calculator in a polar coordinate system or Desmos here, which is really quite helpful when you take a look at these calculations. So that ends the first, I think it will be 2 recorded lectures on section 5.2, and that's graphing and the polar coordinates.